Professor Bialis here. In this video we are going to talk about the start of Chapter 7. Chapter 7 talks about rational expressions and how to work with them. Now really the theme of this chapter is fractions and factoring. Now those are two things that usually cause stress for a lot of people, and now we're going to be combining them. So again, take your time. The beginning part of this chapter should be on the fairly easy side of things. Really work hard to get that down pat, so then later on when it does get a little bit more complex, we're not, scrambling to get all the basic stuff down as well. Okay, so let's get started. This is section 7.1. And we are talking about rational functions and simplifying rational expressions. Really the gist of this section, there are a couple little things in there, but we are going to talk about how to simplify. That's the main idea that we're going to be talking about. Now, before we simplify something, we need to know what the heck it is. So the first thing we're going to talk about is what a rational expression actually is defined as. A rational expression is an expression that can be written in the form P over Q, where P and Q are polynomials and Q is not equal to 0. Okay? Now, this statement should sound familiar. When we talked about rational numbers, that was exactly the same thing, except the P and Q were going to be integers. Okay, now we're talking about polynomials. So a sample of a rational expression could be something like x plus 3 over x minus 7. Those are two binomials, one over the other. The other thing to remember, that Q not equal to 0, we can't have a 0 in a fraction. That's always been the case. That's still the case in these. Okay. Now the other thing that I want to point out is this word can. We don't have to have a fraction necessarily. It just can be a fraction. Okay, so it doesn't mean that we're only working with fractions in this chapter. It's just opening the door for that possibility. Okay, so keep that in mind whenever you're dealing with rational numbers, rational expressions, anything like that. Okay, and another word of advice for the future: whenever you see this word rational, just think fraction. Rational number introduces fraction. Rational expression introduces fractional expressions. We're dealing with fractions here. Okay? So that's what they are. That's what we're going to be dealing with this whole chapter. Let's shift gears into something that is kind of unique to these rational expressions, at least for now. Later on we're going to be applying this idea to other types of functions and expressions, but right now we're dealing with rationals. And that idea is domain. So, I'm going to ask you to find the domain. Okay, now just as a quick reminder, this is something from the past. Domain is basically the set of all included input values. Okay, so if we're dealing with the variable x and primarily in these examples, any number that can be put into x. Now that doesn't mean that it's always going to work out nicely. It's just we have to be able to put it into x. Okay, so let's look at an example. Let's say we have an expression like this. X squared plus 1 over x minus 6. Okay, there's a rational expression. We are trying to decide what the domain of that is. Now, a lot of times when we look for domain, we're looking for, again, what will work. But that's not usually a short list. Okay, that's usually a very long list. What's usually a shorter list is the stuff that does not work. So let's look for that. Now, that brings up the question, when is something not going to work? Look at the definition, or think back to the definition that I just erased on the board. The definition for a rational expression was an expression that can be written as P over Q. P and Q are polynomials. These are polynomials. But then also, Q could not equal 0. Now remember, Q is on the bottom. We cannot have a 0 in the denominator. Okay, so what that means is that this denominator, we want to know when it is equal to 0. Because when that happens, we have a problem. So if we set this denominator equal to 0 and I solve, I get x equals 6. That is a number that I need to avoid because it's going to create a situation that I cannot have. Okay? And that is your restriction on the domain. Now that doesn't mean that this is the domain. This is the restriction on it. So our domain we're going to write in what's called set builder notation. It's a collection of all x's such that x is any real number, comma, x is not equal to 6. And that is your domain statement. A lot of times as we get further and further in mathematics, this statement right here is not written because it's understood. But since this is new, I want you to be writing this out just as a visual reminder that that is part of the statement. So again, it's a set. This brace right here denotes a set of all x values. So I'm going to use all these x values such that, so the rule is, x is any number you want, but not 6. And this is your domain statement. Let's look at another one. How about this? Okay, so same as the last time. When are we going to run into trouble here? We're going to get that when we have that denominator equal to 0. That's going to cause an issue for us. So now we have to solve that equation. Okay, so what we have here is a quadratic. Remember back in chapter 6, we have to factor that. So x squared is x and x. A negative 10 is going to require opposite signs. And I'm going to go with a negative 5 and a positive 2. That'll give me negative 5x plus 2x is the negative 3x. And now I just have to set those equal to 0. This is a prime example of something from the past being utilized in the middle of a new concept. The new concept is that domain where we set this up, but now we have to know how to handle that. Okay, so I subtract the 2, add the 5, and we've got those. Now, again though, be careful, those are not the domain. That's the restriction on the domain. So we are going to say, I'm going to use all x's such that x is any real number. I'm going to use that as a little abbreviation there, comma, x is not equal to negative 2, x is not equal to 5. And there you have it. Okay, let's look at one more like this. How about that? Now what I see a lot of people do is they look at that 4 and they say, well, that's just 4. So I'm going to set x squared minus 9 equal to 0. But that's in the numerator. Remember, the rule is you are trying to find when the denominator is equal to 0. This denominator is never equal to 0. So in this case, there is no restriction. There's nothing we could possibly plug in to cause an issue. It may not come out nicely, but it's going to be workable no matter what we plug in. So in this case, what we're going to do is say that I'm going to use all x's such that x is any real number, period. Notice on all of these problems, you start with this, you start with this, You have that. That is never going to change. If you have a domain problem with a rational expression, that is going to always be part of your answer. What's going to change are these restrictions that follow. And in this case, there was no restriction, so we just stopped there. Okay? That is the idea of domain. Okay, now we will see this again in other situations, in, for instance, square root functions and so on in the future. But right now, we're just sticking with these rationals. Whenever it is a rational, you set the denominator equal to 0, and you find your restrictions. That's all you got to do. Okay, let's move on now. Now let's talk about how to simplify rational expressions. Okay, now just like with normal fractions, simplifying is a very fundamental idea that we need to have down before we can do anything else. Okay, now before we get into the rational expression part with variables and whatnot, I want to just review the general idea of simplifying a fraction. I'm going to keep it very easy. Let's say we have 6 over 9. Now technically that is a rational expression, okay? We call it just a normal fraction typically, but it's a rational expression. Now when we simplified this in the past, a lot of times we would look at it and say, well, 6 divided by 3 is 2, 9 divided by 3 is 3. You just divide those common factors, and that's fine. But why is that the case? What's really going on behind the scenes? What's going on behind the scenes is 6 can be factored into 3 times 2, and 9 can be factored into 3 times 3. Then those common factors reduce out, and we're left with that 2 over 3. These are the mechanics that we really have to do when we deal with polynomials. When it's just a numerical expression, we can just, okay, divide and no big deal. But when there's more to it than that, we have to fall back on this idea here. Okay? Now notice, it's nothing new. It's just something that we kind of take for granted from the past. So we have to reach back and really understand those basic concepts and those fundamental ideas behind what we already know. Okay? So let's look at something more algebraic in nature. Okay, now we have a polynomial expression involved here. Now, what we have to remember is we cannot just reduce terms. We can't do it. I can't reduce these 3y cubes because we have this minus sign. When I reduced those 3's out in the previous example, it was because it was written as a product. I need this written as a product. Okay, and that's exactly what factoring does. Remember, by definition, to factor something means to write it as a product. So that's why I mean, what I meant by this chapter is fractions and factoring. That's really what we're dealing with here. So I am going to factor this denominator. This is already a product. But now I'm going to take a 3y cubed out to get a 2y minus 1. Double check, 6y to the 4th minus 3y cubed, we're good. Now that this is written as a product, I can cancel all that out. Okay? Now, whenever one of the sides of this fraction get cleaned out completely, it clears out to a 1. The reason being, 3y cubed over 3y cubed, anything divided by itself is just a 1. So my reduced or simplified answer is that. Okay? So really all we did was we factored and then we crossed stuff off. That's what it comes down to. Be careful with the factoring. There's nothing new there. Just take your time. Let's look at another one. Okay, now we've got a trinomial over another trinomial. Again, we cannot reduce terms because there's sums and differences in between them. We need products. We can reduce factors, okay? So what we're going to do is simply factor top and bottom. Again, it's coming down to factoring. So let's look at this numerator. I got a 5x squared, that's going to be a 5x and an x, and then I have a 1. Now, it's going to be the same sign, but they're both going to be negative. So I'm going to have minus, minus. Let's just make sure. I got a negative 5x minus 1x gives you that negative 6x. The denominator, I've got 3x and x, nothing really to guess there. And then a negative 7, I'm going to try 7, and 1. I have opposite signs because it needs to multiply to a negative 7. I got negative 3x plus 7x, negative 3 plus 7, positive 4. That's good. Okay. Now, once I have that factored, I can stand back and say, what do they have in common from top and bottom? And that's those two right there. So what I get is that. Okay. Now, later on, if you look at something like this, what they may want you to do is then make a domain restriction statement. But right now, we're just focusing on one thing at a time since this is a new concept. So it is possible to, later on, talk about, this is my expression simplified, but I'm going to restrict the domain this way. We're not going to be doing that here just yet, okay? If you do that, though, just so you guys kind of think about it a little bit, I wouldn't set this denominator equal to 0. I would set this one, okay? Because while this does reduce, if you start here, this is still part of that domain. Okay, so if you do find the domain restriction, you should find the restriction on all of this, not just the simplified form. Okay, again, that's not really an issue right now. I just want you kind of to plant the seed in your head so when that comes later, then you'll know how to handle it. Okay, let's look at a few more of this. Let's say that. Okay. Now, be careful here because when we have 5 plus x, what we're looking at is this binomial and this binomial. If those parentheses help you, put them in there, okay, because it kind of shows you what's being held together. Now, those aren't the same, or are they? In this case, they look different, but they are the same value. 5 plus x, x plus 5, the commutative property tells us those are exactly the same. So in this case, they cancel each other out right away into a what? Into a 1. Simple as that. Now what about this? Are those the same? In this case, no. They're not going to be exactly the same. They're going to be close, but they're not going to be the same. They're going to be opposites. Now, how can I make these the same? Because they are pretty darn close. Okay? What we can do is factor out a negative. Again, they're opposites. So if I want to change the sign, factor a negative out. So what I'm going to do is take a negative out of the top. You could do it on the bottom. I prefer to work in the numerator if I can. And when I take that negative out, this positive 5 turns into a negative 5, and the negative x turns into a positive x. And we're here. Now, if you use the commutative property, this can be turned. Let me just show that to you. Like so. And now those are equivalent. We can cross them out, simplify them out, and what we're left with is a negative 1. So this type of a thing is going to pop up a lot within more complicated problems. Always look out for that. If you have a binomial that's flipped over a negative sign, that's not going to be the same as just flipping it and you're done, okay? If we take out a negative, that then allows us to make that flip. Okay, so that's a little trick that you're going to have to be using from time to time. Okay, so remember that. How about this one? Let me clean up the board here. with this. Same as before, we need to reduce this. In order to reduce, we need to factor. So I am going to go in the numerator and factor this. I've got a 3, and then I have 1 minus x squared. Okay? Now, I want you to start thinking ahead a little bit. We want these things to factor and then match on top and bottom. Notice this is in what's called ascending order. You go from an x from no x up to an x squared. And this is what's called descending order. You go 2, then 1, then nothing. Okay? So the order isn't the same on top and bottom. Let's be a little proactive here. When I took that 3 out, that's fine, there's nothing wrong with that. But what might be a little bit better, watch what I'm going to do. I'm going to take out a negative 3. Just like that previous example, that allows me then to switch over that minus sign. Okay, and I'm going to get x squared minus 1. Okay, and distribute just to show. Negative 3x squared right here, and positive 3 right here. I'm good. Now I'm not done factoring that. I have a difference of squares. And we have that. Let's now go down here. This, I'm just going to go right over here. It has some guess and check. I'm going to have an x and an x. And then it's going to be positive 2, negative 1. And now I can reduce. These cancel. And we're left with that. Now, a lot of people want to distribute that negative 3 after the fact. You can. This is a little nicer though because you're leaving it all laid out and saying, see, there's nothing in common. If you start distributing something back into it, then if you really want to check it, you're going to have to factor it again. Okay, I would prefer and I would suggest just leave it as is. Okay, so how about this? This is a deceivingly simple problem, okay? It looks really, really quick and easy. You just reduce, reduce. But again, if you do that, you're reducing terms, not factors. We can't do that. So we need to factor first. This denominator, x plus 3, is x plus 3. You can't do anything with that. But this numerator, that's that sum of 2 cubes. Let's review that really quick. Whenever you have a sum or difference of 2 cubes, you're going to be looking for a binomial and a trinomial. We start by taking the cube root of each of these. Cube root of x cubed is x. Cube root of 27 is 3. Okay? Next, we are going to take this cube root, square it, multiply these together, square it. And then what do we use for those signs? There's a word. It is SOAP. S-O-A-P. Same, opposite, always positive. And then that denominator again just carries over. Now that we have things factored, cross it out. And what we're left with is that x squared minus 3x plus 9. If you want, that's not wrong. However, try to keep things as simple as you can, because if this is part 1 of 6, you don't want to have too much extra laying around, because then it can complicate things unnecessarily. So while this is fine, that's a little bit better. If that 1 was on the top, you have to leave that there, okay? But if that 1's on the bottom, you can just not write it. It's understood to be there, even if you don't see it, okay? But if you're not sure, just put the 1. If you're thinking, oh, is that 1 necessary or not, just put it there. It's not going to hurt anything, okay? How about this? How about that? Okay, same as always, factor first. We have two factoring problems in one. There's nothing more to it than that. So this numerator, I can take out a 3. I have x squared plus 2. Now the denominator, think back. We have 4 terms. That leads us to grouping. So I'm going to group the first 2 and the last 2. I'm going to do a little bit of side work underneath. I have x squared. Again, I'm just taking a GCF out of these 2. And then here I take out a GCF of 2. Since these match, I can pull that x squared plus 2 together, these 2 GCFs, and then I just write down one of these. And there we have it. We factor top and bottom. That's really where the work is factoring. There's nothing new there. And then, gone. That's the new idea, to do that. That's it. And what we're left with is 3 over x minus 3. Now, again, very dangerous here. Don't reduce these 3's, because this is x minus 3. It's not just a standalone 3. If you find yourself wanting to do that, get in the habit of putting those parentheses on there to at least give you a little bit of a reminder that this goes together. I can't separate those 2 terms. And there's your simplified form. I believe that is it. There is one other idea that they throw at you in this section to just kind of introduce a way of manipulating these expressions. Let's talk about that right now to finish up. So the instruction is list 4 equivalent forms of that. Now, really what this is an exercise in how we can use and manipulate the negative sign on a fraction. Okay? Negatives on a fraction typically in a textbook are written out in front of everything. Now, what that means though is that negative is on either top or bottom. Okay? So it could be written as the negative directly attached to the top, or directly attached to the bottom. Like so. Now, what did I just do? I wrote 2 equivalent forms. Okay, I need 2 more. Now, don't overthink it. What do we have in front of us? If we see a negative with a group following it, we can distribute that negative. So this can be changed into this, and this can be changed into that. And we have 4 expressions. Nothing more than that. Okay, so again, what they're trying to get you to remember and realize here is that a negative out in front can go on the top or the bottom, not on both, because if there's a negative on top and bottom, 2 negatives make a positive. You just changed it. Okay, but top or bottom, distribute, distribute, that's it. When we get into adding and subtracting, we're going to be doing a lot of this, and the one that we're going to be utilizing most often is this one here. Okay, but all 4 of these are perfectly fine, and they can be used given certain situations. Okay, so just as a recap, this section talked about domain. Don't forget about that. That's a very fundamental idea. Then we did a lot of examples of simplify, and then we did this 4 equivalent forms. Simplifying just comes down to factoring. That's really what it is. And then we cross stuff off. Just make sure you're taking your time with the factoring. Don't make a silly sign mistake, because that can throw everything else off after that. Okay? As always, work hard. If you have any questions, let me know, and I'll see you next time.